Hi everybody, this is lecture 2.7, Math Models. This is where we start getting into the word problems for this unit. We are going to take notes on pages 16 and 17 of the student note packet. And you also need a graphing calculator. So find your graphing calculator or use Desmos if you need. Doesn't matter which one, you can use either on a test. But we're going to use that for a couple of the problems here, and then you'll do the homework very similarly. Okay, so we're going to start kind of going out of order on pages 16 and 17. Take a look at page 17. Find number 15, which is the bottom problem on page 17. We're going to start there and then kind of work our way around. So we've got the situation. We've got a semicircle of radius r. It's inscribed in a rectangle so that the diameter of the semicircle is the length of the rectangle. And we've got a picture there. And the first question is this: we want to express the area of the rectangle as a function of the radius. So we need to find an equation that represents the area of this rectangle in terms of r. So we want the equation to be in terms of the radius and only the radius. We only want one variable there. So let's take a look. We know something about the radius. We know that the radius, or a radius of a circle or semicircle, is the length between the origin and a point on the exterior of the circle. So we have a radius drawn in for us on that diagram, but it's a little bit misleading, or it's not quite obvious that that's also radius. This is also radius, and I can also drop a radius perpendicular to the base there as well. And we call that r. So that actually gives us a little bit more of an idea of what the base and the height of this rectangle are in terms of the variable r. So I know that our base is 2 r's and our height is a single r there. So when we go to express the area of this rectangle, the area of the rectangle here in terms of r is base times height. It's 2r times r, which we can simplify to 2r squared. All right, the next piece then is asking us to find the perimeter of this rectangle in terms of r. So if we think about perimeter, think back to geometry. Perimeter is always 2 times the base plus 2 times the height. So the perimeter in terms of r is just 2 times our base, which is 2r, plus 2 times our height, which is 1r. That gives us a total of 6 r's for the perimeter of this rectangle in terms of r, the radius of that semicircle. All right, the next problem we're going to do is number 6, which is on the bottom of page 16. So go find that. We've got the situation. We've got a right triangle that has one vertex on the graph of y is equal to 9 minus x squared. I'm just going to highlight what's important here. We also have a domain restriction that we'll keep in mind. So we're only going to be graphing the positive x values of that parabola. So only everything to the right of the y-axis. Okay, so one of the vertices of our triangle is on that parabola. We'll call that point xy, wherever it touches. Another vertex is at the origin, and a third one is on the positive x-axis at some point x0. We want to express the area of this triangle as a function of x. So let's kind of draw the situation, and then we'll go from there. Let's sketch the parabola first. We've got a downward-facing parabola whose vertex is 9 units up on the y-axis. So if I go up 9, I've got my vertex here, and then a downward-facing parabola means we move right 1, down 1, right 2, down 4, right 3, down 9, and that's our parabola. Now remember that domain restriction where it says x must be greater than 0 means I only care about the right-hand side of that parabola. We're not graphing any of the negative x values. All right, so we've got this parabola, and then we're told the following. We have a triangle with 3 vertices. One of those vertices is on the origin. That comes from that. A second vertex is on the x-axis at some arbitrary point x0. So I'm just going to pick a point on the x-axis. That sounds like a good point. And I'll call that x0. Don't know what it is. I don't know what the numerical value of x is. That's the point here. And then the third and final vertex of this right triangle is on the parabola at the point xy. So here's the deal. These 2 vertices have the same x value. So that means that our third vertex is going to be directly above the point on the x-axis, right? The point on the positive x-axis. That's the only way that those 2 points can have the same x-coordinate. is if they're at exactly the same x location. And so when we've got all three of these points together, we've got our right triangle. Now the point of having that arbitrary point x0 and that arbitrary point xy is the following. I could have picked any point on the positive x-axis between the origin and the parabola. I could have chosen this point to be x0, which means that this would have been my right triangle. Would have been tall and skinny. I could have picked this point out here to be my point x0. So I would have had a lot shorter of a right triangle, but kind of wider along the base. I could have picked this point and made this triangle. So there is a large amount of right triangles that we could have drawn that fit all of this information that we're given. And the point is that we're finding an equation to help us express the area of any one of those possible right triangles that we could have drawn in there. Right? So that's our math models. That's kind of what we're getting into. And we'll come back to stuff like this when we get into the conics unit next semester as well. So we want to express the area of this triangle as a function of x, so just in terms of x. But think back to geometry. Let's kind of start with the basics. We know that the area of a triangle is always base times height. So let's find a way to represent the base and the height of this triangle. Now, sometimes we might not be able to jump directly to only in terms of x. Let's think about what we know. Well, the base of this triangle is x, because to get from the origin to the point x0, I have to move x units to the right. And the height of this triangle, well, the height of this triangle is y, because I move up y units to get from the point on the positive x-axis to the point on my parabola. So the area of this triangle in terms of x and y is just 1/2 xy. The area up here should be 1/2 base times height. Okay, definitely know the area of a triangle. All right, but this is the problem. The problem asks us to express the area of a triangle as a function of x and x alone. Right now, what we've got in orange has x and y. The reason for that is in the next example, we're going to use a graphing calculator to graph this function. And a graphing calculator will not allow us to graph things in terms of x and y, only one variable. So we've got to get used to that. So I've got to find a different way to express this area equation only in terms of x and x alone. So we think about it, we go up to the top problem, and there's a way to express y in terms of x. Because our third vertex is on the parabola, we have an equation that equates y and x. Y is equal to 9 minus x squared. I can substitute 9 minus x squared everywhere I see x, or y, and that will give us an equation only in terms of x. So we can replace y with 9 minus x squared from the equation of the parabola, because we know that the third vertex lies on the parabola. That's why we're allowed to substitute. All I'm going to do here then is I'm just going to simplify this up a little bit. I can leave the half out and I can just distribute the x. You could distribute the half x, doesn't matter to me, just simplify it a little bit. That looks good for me, and that's the final answer for this problem. So then what's next is going to be number 1 on page 16, so the very top. We're going to apply the same sort of idea from number 6, but we're going to be using our graphing calculator to take it a little bit further. So the first thing you need to remember is the distance formula. There's a line at the top of your note paper on page 16 to write the distance formula in. This is the equation to find the distance between 2 points. You just take the difference of the x values and square them, add them to the difference of the y values of the ordered pairs and square them, and then take the square root. We're going to use that in just a minute. So here's the problem. Number 1, top of page 16, we've got this point xy, and it's on the graph of x squared minus 8. It's another parabola. We've got a point on that parabola. And here's the question. We want to find an equation that expresses the distance from any point on that parabola back to the origin. And we want that equation only in terms of x. So that's our goal. So let's sketch it, see what happens. We have got an upward facing parabola whose vertex is down 8 units along the y-axis. So let's count 8 units out along the negative y-axis. There's our vertex. Upward facing because x squared is positive, so standard stretch of 1, right 1 up 1, right 2 up 4, right 3 up 9, and then I will reflect those points over the y-axis. And that's our parabola. Okay, so then our goal here for this problem is this. We want to find an equation that expresses the distance from the origin to any point on this parabola. So pick a point on this parabola. I'm going to call that point 1. I want an equation that represents that distance. But I could pick any point. So what if I had picked this point instead? Or what if I had picked this point instead? We are looking for an equation that will represent any of those distances based solely on the variable x. All right, so that's our goal. So we're going to use the distance formula. We know two things. We know that the point has the coordinates x, y, and we know that the origin has the coordinates 0, 0. So if we use those two ordered pairs in the distance formula, we've got an equation in terms of x and y. All right, so distance formula tells us we take the difference of the x values and square them, add them to the difference of the y values and square them. Our equation for distance in terms of x and y is then x squared plus y squared. But that's not good enough because we have to get this equation only in terms of x. We're asked to write it as just a function of x, not x and y. And we're going to use a graphing calculator in a minute. We won't be able to plug that in. So we've got to think about how we could substitute y. Do we have a way to represent y in terms of x? And we do. Just like the last problem, we have an equation here that equates x and y. Y is x squared minus 8. We can use that substitution because we're taking a point on the parabola x squared minus 8. So now I can represent this as just an equation for distance in terms of x and x alone. I'm going to take y and I'm going to replace it with the quantity x squared minus 8. Now, remember, we're squaring that because y is being squared, so we have to FOIL and do some simplifying. So when I FOIL x squared minus 8 squared, we end up with the square root of x squared plus x to the 4th minus 16x squareds plus 64. And then I've got to combine like terms here. So when I combine like terms, we end up with our final answer as x to the 4th minus 15x squareds plus 64. That is our distance equation in terms of x and x alone. So next piece, part B and C asks us this, and we can do these without a calculator. What is the distance if x is 0? So when x is 0, what is the distance? So we're going to replace x with 0 in the equation, and we're going to evaluate. So when x is 0, we get the square root of 64. Now think about this. Technically, this is plus or minus 8. However, our function represents distances from a point to the origin. We never measure distance with a negative number, so we are only going to take the positive value of 8. And this tells us when x is 0, the distance from the origin to our parabola is 8 units. Now if we look at it graphically, if you look at the graph up above, where on the graph is there a point with an x-coordinate of 0? Well, it's down here at the vertex. The x-coordinate of the vertex is 0, and the distance from the origin to that point is 8 units. We move down 8 units from the origin. So that lines up with what we've got. The next piece then, what is the distance if x is 1? So when I replace x with 1, what do we get? We get the square root of 1 minus 15 plus 64. We get the square root of 50, which can simplify to 5 root 2, which is about 7-ish units, 7.07 units. And graphically, what that represents, do this in a different color, where is there a point on the parabola whose x-coordinate is 1 this time? Well, when x is 1, we're at this point here. The distance from that point to the origin is that 7.07 units. That's what that equation allows us to do. pick any point for x or any value for x, we can find the distance from that point on the parabola to the origin. Next step then is to use our graphing calculator. So pull your graphing calculator out. You guys are going to hit the y equals button, and I have this plugged in already, but we're going to type in the equation for distance. That's square root of x to the fourth minus 15x squared plus 64. Make sure you guys have no typos there, otherwise you'll get a weird looking graph. And we're going to hit graph on our graphing calculator. So go ahead and hit graph, and that's what it looks like. So we are going to sketch that, and it's going to be a very, very, very rough sketch. But before we do that, let's talk about E. All right, so E, the last piece asks us this: for what values of x is the distance the smallest? So remember, we just graphed the function that represented distance. So all of those y values that we see on that graph represent the various distances from any point on our parabola back to the origin. We're looking for where D is the smallest. So we're looking for the minimum value that we see. We're looking for one of these. We're going to trace that with our calculator, and then we'll do our sketch and everything else. All right, so think back to Algebra 2 when you guys did this on the calculator. You're going to hit second trace. Second trace gets you to this calculate menu, and you're going to go down and select minimum. That's what we're looking for here. Hit enter. You're going to get that blinking cursor, and you need a left and a right bound. So drag the blinking cursor somewhere to the left of that minimum, hit enter, and then you're going to drag the cursor using the arrow keys somewhere to the right of that minimum, hit enter again. And those two lines should encompass your minimum. Your minimum value we're looking for should be between those two bounds. Hit enter for the third time, and your cursor is going to move straight to that minimum value. All right, then we're going to put this all together. So I'm going to sketch this, and then we'll go from there. Here's what I mean by sketch. I just want a really rough curve, okay? That's it. And the only thing you have to do is give me one thing that denotes the scale. So this minimum here was 2.7386, comma 2.7839. That's it. Rough sketch. But what does this represent? Well, remember our function was in terms of x, so the x value is just x. But the y values represented the distance. So here's how we're going to answer that final question. For what values of x is D the smallest? Well, when x is equal to 2.7386, the distance from the point on the parabola to the origin is the smallest at 2.7839 units. All right, there's one more thing I'm going to change or add to this answer, and that is this. If we took a look at our graph, we found the minimum in the positive or in the first quadrant. There's also a minimum over here. Because our parabola could have a negative x value, we can graph negative x values on the parabola. We're going to make sure that we include in our final answer when x is plus or minus 2.7386. X can be negative. Distance can't be, but the distance is represented in the y values, not the x values. So we'll make sure we express it as positive or negative 2.7386. Okay, our very last problem to introduce math models is this. And I need you guys to think about this visually. So we have a wire or a string, and it's 10 meters long. So imagine you're holding a string that is 10 meters long, and you cut it in two places, and it doesn't matter where, like you don't necessarily cut it in half, but you just cut it so that you have two pieces of string. You're going to take one piece of that string, and you're going to shape it into a square, and the other piece of that string we're going to shape into a circle. So you take a piece of string, cut it somewhere, make a square, make a circle. Okay, we've got a diagram here also to kind of help us visualize that. We want to express the total area that's enclosed by these pieces of wire, these pieces of string, as a function of the length of x, which is a side of the square. All right, so we need to find a way to represent the area of both that circle and that square in terms of x. Now, we define x in this problem as the side length of the square. So the square, right, if we call it a side length of x, that means that we cut 4 x's off of one side of our string to make that square. It took 4 x's of length to make that square because the perimeter of the square is 4x. All right, then the remaining amount, remember that we started with 10 meters. If we take 4 x's away, sorry about that, my dog saw the mailman. Okay, so what's left is then that 10 minus 4x. That creates the circle. And if we think about that, that's the circumference of the circle. So the circumference of this circle is equal to that 10 minus 4x. The length of the string left over after we take 4 sides of a square away. So we want to express the total area enclosed by these pieces of wire in terms of x, but let's just think about the area in terms of what we know from geometry first. So we've got the area of a square, which is just base times height, right? And then we have to that, the area of a circle, which is pi r squared. So that's kind of it in terms of geometry. Now let's start thinking about it in terms that we've already got. Okay, so I know what the area of the square is. The area of the square is just x squared, right? Side lengths both are x. But we have to find a way to get r in terms of x. So that's going to be the tricky part here. Now, we know something about the circumference of the circle. We know the circumference of the circle is 10 minus 4x. So if we can remember the circumference equation from geometry, we can start looking for a way to relate x and r. So if you think back to geometry, 2 pi r, or pi times the diameter, was the circumference of a circle, and we know that our circumference is 10 minus 4x. So what we're trying to do is we're trying to get r in terms of x. I need to find a way to get r by itself and only in terms of x. So I'm just going to divide both sides by 2 pi, and then we've got r by itself. R is equal to 10 minus 4x over 2 pi. Now, always want to make sure that everything is simplified. I can take a 2 out of all those terms and end up with 5 minus 2x over pi. Now we have r in terms of x. I can go ahead and replace r in our area formula with 5 minus 2x over pi and then see what happens. So to that, we're going to add, let me do this in the right color, pi times the quantity 5 minus 2x over pi squared. And of course, we're going to simplify. The x squared stays out here, but what I can do is if I were to FOIL or square everything inside the parentheses, we would end up with pi squared on the bottom and then a pi on the top. So what happens is we are left with 5 minus 2x squared over a single pi in the bottom. Okay, and I'm going to leave it like that for the sake of time. So let's move on. The next piece is this. We want to know what the domain of A is, and then we're going to graph it with our graphing calculator. So let's think about the domain of A. A is written in terms of x, where x is the length of a string, right? Or piece of the length of a string. So we are limited in our domain because x can't be greater than the length of the wire we have. We can't have more than 10 meters of wire because that's all we had. We were given 10 meters, and that's it. So I know that our string is limited to that length, and it's also limited by 0 as well. So we can't have a string or a wire with anything less than 0 in length. And we can't have anything bigger than 10 meters on the upper bound. But what is it that has to be between those two values? Well, in order to make a square, we need 4 sides. So we need 4 x's to make a square. If we can't make a square, then we can't follow the rules of this problem. And so this is how we're going to get the domain. We're going to just solve for x. We're going to divide both sides by 4. And what happens is x lies somewhere between 0 and 5/2, or 2.5. All right, and that is our domain. We must have a circle, we must have a square, which is why it's not equal to 0 or equal to 2.5. We have to be able to make two shapes, a square and a rectangle. Otherwise, we can't follow the rules of this problem. And we need 4 sides of that square, so that's how we get that 0 and that 2.5. All right, so the last thing we're going to do is graph this in a graphing calculator, and for that, I have to clear all of the work, so pause if you need more time on this. We're going to move over to the graphing calculator, and I have graphed, or I've typed in this equation already. So we are graphing x squared plus the quantity 5 minus 2x, that squared over pi. Here's a little trick. If you've got a newer TI-84, if you hit alpha y equals, so the green button y equals, you can get a fraction button, and that's how you get the output like mine. If not, just make sure your parentheses are in the right spots when you guys are typing in fractions. And we're going to hit graph. And this is what we got. We got this like parabola that's kind of moved, and we're going to sketch that in just a minute. But we want to know for what values of x is a the smallest. Remember, this equation that we just graphed represents the area of the square and the circle. So we want to find what values of x yield the smallest area. So let's find that minimum. So again, second trace, go down, select minimum. You can also just type in 3. And we're going to drop a left bound, hit enter, and then we're going to move the cursor over, select some right bound, make sure that that minimum is somewhere between those two lines, hit enter for the 3rd time, and there we have our minimum value. So we're going to sketch that, and then we're going to interpret it. All right, now think about this. X. We had a domain restriction for x. We know x has to be somewhere between 0 and 2.5. So that means that we are not graphing anything to the left of the y-axis. That is out. And we're not going to graph anything beyond 2.5 either. So kind of do your best there. And then literally just a really, really rough sketch like that. All right, and I can clean up those edges so that I don't cross the y-axis there. And all I need you guys to do is mark a single point. So we're going to just mark the minimum, and that gives me kind of your scale for the sketch. And we've got this. The x value 1.4002, and the y value is going to be 3.500. Okay? And let's think about what that function was. Well, it took values of x as the input, and it yielded area as the output. So all those y values represent the possible areas that we could get with a 10-meter wire creating a square and a circle. So our final answer for part C, we've graphed it, we've sketched the graph, we've labeled that minimum value. For what value of x is a the smallest? Well, when x is equal to 1.4002 meters, that's our unit. Area is the smallest at 3.5 meters squared. And we'll leave it like that. All right, so that is an intro into math models. We will continue working with those, and then when we get to conics, we'll be doing this in a little bit more of a complicated way. But get started on the homework.